in the velvet hush of a winter's night, far from the orange glare of cities, we lie back upon the cool grass of an English meadow and allow our eyes to surrender to the darkness. Above us, the Milky Way arches like a river of frost fire, a faint silver band strewn with the dust of 100 billion suns. It has hung there for almost the entire history of humankind, unchanging to the naked eye, a quiet promise that some things, at least, are eternal. Yet tonight, in the slow cadence of thought that precedes sleep, we permit ourselves to travel forward, far forward, 4 billion years, perhaps a little more, to the moment when that familiar ribbon of light will be torn apart and reborn. The end will not come with a bang, nor with the sudden violence we once feared, but with a vast, inexorable inhalation, as though the cosmos itself were drawing one long, final breath before everything we have ever known is gently, irrevocably transformed. Together we drift outward, past the familiar lantern of the moon, past the watchful planets, past the cold wanderers of the Kuiper Belt, until the sun itself dwindles to a spark among countless others. We are no longer bound to the present. We glide along the inexorable arrow of cosmic time. Ahead of us, vast and serene, lies the great pinwheel of the Andromeda galaxy, M31 in the old catalogues, 2.5 million light-years distant, yet moving toward us with the quiet certainty of tides. For decades, astronomers believed the two galaxies would pass like ships in the night, their gravitational embrace too weak, their relative velocity too high. Then, in 2012, the Hubble Space Telescope's meticulous measurements of proper motion, published by van der Marel and his colleagues in the Astrophysical Journal, revealed the truth we now take almost for granted. Andromeda is falling almost directly toward us at some 110 kilometers per second. There will be no glancing blow, no polite sidestep. In approximately 4 billion years, give or take 100 million, the Milky Way and Andromeda will meet face to face in the slowest, grandest collision the local group has ever witnessed. Let us linger for a moment on that timescale. 4 billion years ago, the Earth was a young world still cooling from its molten infancy. The first continents were only beginning to wrinkle the surface of a global ocean, and life, if it existed at all, was no more than simple prokaryotes huddled around volcanic vents. In another 4 billion years, our sun will have swollen into a red giant, its outer envelope perhaps engulfing the scorched remnants of Mercury, Venus, and possibly Earth itself. Long before that gentle stellar cremation, however, the sky will have changed beyond recognition. The constellations we cherish, Orion, the Plough, the Southern Cross, will have been deformed and scattered as the gravitational architecture of our galaxy is rewritten by an intruder 4 times more massive than ourselves. Imagine, if you will, the view from a hypothetical planet still orbiting a sun-like star in the outer suburbs of the Milky Way, some 3.5 billion years hence. The night sky remains comfortingly familiar at first. Andromeda still appears as a faint, elongated smudge in the constellation that once bore its name. But century upon century, the smudge grows brighter, larger, until it dominates the heavens like a second Milky Way, strangely tilted, its spiral arms clearly visible to the unaided eye. By the time the two galaxies are separated by no more than a few 100,000 light-years, tidal forces begin their patient work. Great streamers of neutral hydrogen, traced in the 21-centimeter line by radio telescopes we can scarcely imagine, are pulled from the outer disks of both galaxies, forming luminous bridges that glow softly in the ultraviolet. The gas is compressed, shock-heated, and within those vast filaments, the first new stars of the coming age begin to ignite, fierce blue-white beacons announcing that the merger has truly begun. The most recent simulations, those released jointly by NASA and the European Space Agency in 2024, and refined further by the illustrious TNG collaboration, paint a picture both cataclysmic and strangely serene. We watch, half dreaming, as the two great disks interpenetrate. Individual stars, separated by distances of light years, almost never collide. The mean distance between neighbors is so vast that the stellar population passes through one another like phantoms. Yet gravity is not so courteous. As the dark matter halos of the two galaxies overlap and merge, dynamical friction drags the cores inexorably together. Spiral arms are wrenched outward into tidal tails, hundreds of thousands of light years long. Graceful arcs of starlight that will take 1 billion years to dissipate into the intergalactic void. The barred spiral structure of the Milky Way, so proudly displayed in infrared surveys by the Spitzer and now the James Webb Space Telescope, is disrupted beyond recovery. In its place, vast ripples propagate through the disk, triggering a frenzy of star formation wherever dense molecular clouds are squeezed by passing density waves. And here, in the midst of apparent chaos, nature performs one of her most exquisite conjuring tricks. The sudden influx of fresh gas, stripped from the outer reservoirs of both galaxies, feeds the central regions. Starburst rings ignite around the coalescing nucleus, rings that shine with the luminosity of 100 billion suns. The supermassive black holes at the heart of each galaxy, our own Sagittarius A, with its modest 4 million solar masses, and Andromeda's considerably heftier beast of perhaps 100 million, begin a long gravitational waltz. They circle one another ever more closely, shedding orbital energy by flinging nearby stars outward at hyperbolic speeds in a process known to astrophysicists as three-body scattering. Eventually, within a few tens of millions of years of the closest approach, the two black holes merge in a thunderclap of gravitational waves, an event that will ring across the cosmos at the speed of light, detectable perhaps by the successors of LISA, the Laser Interferometer Space Antenna, due for launch in the 2030s. Yet even this titanic union is not the finale. As the dust settles, literally and figuratively, over the course of another 1 billion years or so, the newly combined galaxy begins to relax toward a new equilibrium. The wild distortions smooth themselves out. The long tidal tails rain back onto the central body, adding their gas and stars to the growing whole. What emerges from the wreckage is neither the Milky Way nor Andromeda as we knew them, but a vast elliptical galaxy, smooth and featureless to visible eyes, glowing with the mellow light of ancient red stars. Astronomers have already bestowed a name upon this future behemoth, Milkomeda. Some prefer Milkomeda. Both are provisional, affectionate placeholders for a galaxy that no human eye will ever directly behold. Let us pause here, suspended in the slow-motion grandeur of it all, and consider what this means for the night sky of that distant epoch. Long before the final coalescence, when the two disks are still distinct but heavily distorted, an observer on a surviving planet would witness a celestial fireworks display unlike anything in recorded history. The sky would blaze with supernovae as massive stars, born in the compressed gas of the starburst, live fast, and die in spectacular explosions. Novae would pepper the heavens as white dwarfs in close binary systems are fed fresh hydrogen from swollen companion stars disturbed by the changing gravitational potential. The merged nucleus would host an active galactic nucleus for perhaps 10 million years, a quasar-like beacon briefly outshining everything else in the local group. And overhead, the distorted remnants of both spiral arms would form luminous arches and bridges, creating a sky so bright that true darkness might never again fall upon the night side of any world. Yet reassuringly, the sun itself is likely to emerge relatively unscathed. Detailed N-body simulations, such as those published by Cox and Loeb in 2008 and updated with Gaia data by the Eagle and Auriga teams, suggest that our star, currently residing some 27,000 light-years from the center, will be flung outward during the merger to a new orbit perhaps twice as distant from the eventual core of Milkomeda. The gravitational perturbations will be profound, but the probability of a close encounter with another star sufficient to disrupt the orbits of the planets remains vanishingly small, less than 1 in 100,000 over the entire multi-billion-year process. Life, if it has endured the sun's red giant phase by migrating outward to the habitable zone around a cooling white dwarf, or by some more audacious engineering we can scarcely conceive, may yet persist beneath a sky utterly transformed, yet still filled with light. We drift now, gently, through the later phases of the merger as depicted in the 2024 NASA/SA visualization that has become almost iconic among professional astronomers. The viewpoint pulls back. The two galaxies, once separate entities, are now a single chaotic maelstrom of light and gas. Vast bubbles of ionized hydrogen, carved by the winds of newborn O-type stars and the jets of the coalescing black holes, glow in shades of rose and emerald. The central regions have settled into a smooth, golden ellipsoid, while the outer reaches still display faint tidal debris, like the lingering contrails of an immense aircraft. Slowly, inexorably, even those fade. By 8 billion years from the present, Milkomeda has assumed its final form, a giant elliptical galaxy, one of the largest in the still youthful Virgo supercluster, its stars orbiting in random inclinations, its interstellar medium depleted, its spiral arms a memory preserved only in computer reconstructions. And so, as our eyelids grow heavier, we find ourselves returning, almost reluctantly, to our own epoch. The meadow beneath us is damp with dew. Somewhere, an owl calls. The Milky Way still arches overhead, serene and untouched. 4 billion years is a time span so vast that the entire rise and fall of mountain ranges, the opening and closing of oceans, the coming and going of ice ages, are mere punctuation marks within it. The collision with Andromeda is not a catastrophe in any ordinary sense. It is, instead, a metamorphosis, the next chapter in the biography of the galaxy that cradled our species from its first spark of curiosity to the moment we first looked up and wondered. Yet even this majestic union is only the beginning of the story we have come here tonight to tell. For beyond the birth of Milkomeda lie threats of a different order, the slow chilling of the stellar population as star formation ebbs away, the inexorable growth of the central black hole, the eventual ejection of our descendant galaxy from the local group altogether, and on timescales that make 4 billion years seem an afternoon, the profound loneliness of the degenerating universe itself. But those are tales for another night, for other parts of this long journey through the dark. For now, let the image of those two great galaxies, locked in their slow gravitational embrace, linger behind your closed eyes. Let the knowledge that the sky above you is already, imperceptibly, falling toward its partner across the void bring not fear, but a profound sense of belonging to something far larger than ourselves. We remain for a little longer beneath that same quiet English sky, the grass cool beneath our shoulders, the Milky Way still perfect and unbroken above us. Yet even as the after-image of Milkomeda's distant birth fades gently from the mind, another presence makes itself felt in the darkness, something far closer, far stealthier, and infinitely more intimate in its menace. While the great collision with Andromeda is a drama written in the language of billions of years, there are dangers abroad tonight, dangers that drift unseen through the halo of our galaxy like silent predators in an ocean of stars. They have no light of their own, no heralding glow. They announce their existence only when something unwary falls too near and is torn apart in a brief, terrible flare. We speak, of course, of rogue black holes, stellar mass graves that wander the vast spaces between the spiral arms, exiled from the clusters that birthed them, free to prowl the galactic halo almost undisturbed. Let us descend now, not forward in time, but inward in imagination, down through the familiar disk where the sun and its neighbors orbit in orderly procession, down past the thin gaseous veil of the Gould Belt, until we reach the immense and almost empty sphere that encloses everything, the galactic halo, a region stretching 500,000 light-years in every direction, populated by ancient globular clusters, by streams of disrupted dwarf galaxies, and by a population of dark objects whose numbers we are only now beginning to guess. It was long believed that black holes, once formed in the fiery deaths of massive stars, remained politely bound to the open clusters or OB associations of their birth, or at the very least stayed within the disk where star formation is vigorous. Yet nature, as is her habit, has proved more untidy than the textbooks once allowed. In 2023, a team led by Harvard's Kareem El-Badri and Avi Loeb, building upon earlier work with Gaia data and the exquisite astrometry of the Hubble Space Telescope, published a careful census in the monthly notices of the Royal Astronomical Society, suggesting that the Milky Way may harbor not merely a handful, but between 10 and 100 truly rogue black holes of stellar mass drifting through the halo. These are not the gentle 4 solar mass objects we once imagined remaining quietly in the plane. Many, perhaps most, received violent natal kicks of several hundred kilometers per second when the supernova that created them exploded asymmetrically. Ejected from their birth clusters at speeds greater than the local escape velocity, they were flung outward like stones from a sling, condemned to wander the halo for the remaining 10 billion years of the galaxy's life. Together we picture one such wanderer, a black hole of perhaps 12 solar masses, its event horizon no wider than the orbit of Mars, yet containing within that tiny sphere a curvature of space-time so profound that light itself can no longer escape. It moves against the distant background of halo stars at 300 kilometers per second, silent, invisible, detectable only by the subtle deflection of starlight as it passes, a gravitational microlens that betrays its presence for a few weeks or months before the alignment breaks and darkness swallows the evidence once more. The Gaia mission, in its final data releases, has already found dozens of candidate events whose light curves refuse to fit the signatures of ordinary stars or binary systems. Some, when followed up with the formidable resolving power of the Keck telescopes or the Very Large Telescope in Chile, reveal no visible companion at all. The lens, it seems, is truly black. These rogues are not evenly distributed. Many follow highly eccentric orbits that carry them from the innermost bulge out to the halo and back again every few 100 million years, like comets around the sun. Others, kicked even harder, have achieved escape velocity entirely and are already leaving the galaxy forever, bound for the emptiness between the local group members. The Harvard study estimates that at any given moment, several dozen remain within the volume occupied by the visible disk, passing through the spiral arms once every few tens of millions of years. The probability that one will come close enough to the solar system to disturb the Oort cloud within the next billion years is small, perhaps 1 part in 1,000, yet not zero. And on the longer timescales we have grown accustomed to contemplating tonight, the cumulative risk becomes uncomfortably real. Imagine, if you will, the consequences should such an object pass within 1,000 astronomical units of the Sun, roughly the distance to the inner Oort cloud. The gravitational perturbation would be subtle at first, a gentle tugging on the distant comets, a fractional increase in their orbital eccentricities. Over tens of thousands of years, however, those small nudges would cascade. Comets that have slept undisturbed since the formation of the planets would be shaken loose, sent spiraling inward on orbits that cross those of the terrestrial worlds. The night sky of Earth, or whatever Earth has become, would fill with new and brilliant comets, their tails stretching across half the heavens. Some, inevitably, would strike the atmospheres of planets still capable of bearing oceans or air. The late heavy bombardment of 4 billion years ago, which scarred the face of the moon and may have delivered the water we drink tonight, would be replayed on a smaller but still catastrophic scale. Yet even this is not the worst that a rogue might do. Should one pass within 100 astronomical units, still a vast distance, but not impossible over the age of the galaxy, the perturbation becomes severe. Neptune and Uranus could be ejected entirely. The orbits of Jupiter and Saturn might be driven into resonance instabilities that fling one or both giants from the system. The inner planets would suffer chaotic changes in eccentricity, turning stable circular orbits into wild ellipses that alternately freeze and scorch their surfaces. Life, if it clings on in deep subterranean refuges or in engineered habitats, would face an existential challenge far more immediate than the slow brightening of the sun. We must not allow these somber thoughts to disturb the quiet rhythm of our breathing, for the timescales remain generous and the probabilities low. The same simulations that predict 10 to 100 rogues in the halo also reassure us that the mean time between close encounters within the solar system's volume is measured in hundreds of billions of years, far longer than the current age of the universe. Nevertheless, the knowledge that such objects exist at all has shifted our understanding of the galaxy's darker inventory. The microlensing observations in astrophysics, MOA, collaboration, and the optical gravitational lensing experiment, OGLE, at Las Campanas, have together recorded thousands of microlensing events toward the bulge. The fraction that may be due to free-floating black holes rather than dim stars or brown dwarfs is still debated. but estimates from 2024 analyses by Lam and Liu at Berkeley suggest up to 20% in some lines of sight. If correct, the halo population could be nearer the upper end of the Harvard estimate. There is a peculiar poetry in these silent travelers. Each carries within it the memory of a star that once burned with the ferocity of 1,000 suns, a star that illuminated its surroundings for a mere 10 million years before collapsing into singularity. Now, billions of years later, that same mass moves through the darkness without friction, without sound, without any interaction save gravity. They are the galaxy's monks, cloaked and hooded, keeping to the loneliest roads. And yet, like monks, they are not entirely harmless. Their passage can still bring upheaval to those who dwell in the brighter, busier regions nearer the disk. As the years of the 21st century give way to the 22nd and beyond, our descendants, or the instruments they leave behind, may develop the means to detect these rogues long before they become dangerous. The Nancy Grace Roman Space Telescope, with its wide-field infrared vision, and the Vera Rubin Observatory's relentless synoptic survey from Cerro Pachon, will map microlensing events across the entire sky with unprecedented precision. Astrometric wobbles measured by the successors of Gaia may reveal the closest examples decades in advance. Should one be found on a collision course with the inner solar system, there will be time, centuries, perhaps millennia, to prepare. Whether that preparation takes the form of gentle gravitational nudges from future spacecraft, or the wholesale migration of civilization to the outer moons, or simply the stoic acceptance that all things must pass, we cannot yet say. For now, in the gentle dark of an English night in the early 21st century, the rogue black holes remain invisible, unknowable, and therefore strangely comforting in their distance. They remind us that the galaxy is not merely the pretty spiral we see in long exposure photographs. It is also a vast, half-empty cathedral of dark matter and darker objects, where the light we cherish is only a thin frosting on an immense and hidden architecture. Somewhere out there, one such wanderer may even now be crossing the plane of the ecliptic 1,000,000 light-years beyond Pluto, its gravity brushing the outermost comets like a hand passing over harp strings too distant for us to hear the note. Let that thought settle, soft as thistledown, as we feel the slow turning of the earth beneath us. The meadow is quiet, the stars keep their ancient stations, and the rogue black holes, like the great merger still to come, are simply part of the long, slow music of the Milky Way's life, a music that began 13 billion years ago and will not fall silent for tens of billions more. The meadow has grown cooler now. The dew has begun to silver the grass, and the faintest suggestion of frost glimmers on the gatepost. Above us, the great wheel of the galaxy turns with imperceptible majesty, and yet, even in this quiet hour, there is a tension in the air, the sense that somewhere, very far away, something is poised to scream. We have spoken of slow collisions and silent wanderers, of dangers measured in hundreds of millions of years, but tonight we must admit a swifter, more merciless possibility, that the Milky Way contains within its spiral arms the means of sudden, blinding annihilation, an event so brief that it would be over almost before the light reached us, yet so violent that it could strip 1,000 worlds of their atmospheres in the blink of a cosmic eye. We speak, of course, of the gamma ray burst. Let us drift together, gently, to the outer reaches of the constellation Sagittarius, where the sky is richest in massive stars. Here, some 8,000 light-years away, lies a system that has quietly haunted the dreams of astronomers since its discovery in the closing years of the 20th century. WR104, a Wolf-Rayet star, locked in a deadly embrace with what is probably an equally massive companion, both orbiting one another in a mere 241 days. Wolf-Rayet stars are rare and terrible creatures, sun-like cores laid bare after the outer envelope has been blasted away by ferocious stellar winds, revealing a surface hotter than 50,000 Kelvin and glowing with the fierce chemistry of helium, carbon, and oxygen. They live only a few 100,000 years, and when they die, they do not go quietly. In March 2008, a team led by Peter Tutil at the University of Sydney, using the infrared capabilities of the Keck telescopes atop Mauna Kea, revealed something extraordinary about WR104. Its winds do not stream away uniformly. Instead, they collide with the wind of the companion to form a dense, rotating disk of gas and dust that spirals outward in a perfect glowing pinwheel. From our vantage point on Earth, the axis of that pinwheel points almost directly toward us, within 12 degrees of exact alignment, an orientation that has not shifted appreciably in the intervening years. The implications are chilling. When one of these stars, most likely the Wolf-Rayet component, finally exhausts its fuel and collapses, the core will rebound in a supernova of staggering violence. In a fraction of those cases, perhaps 1 in 1,000, the collapsing star possesses exactly the right combination of mass and spin to channel a significant fraction of the released energy into two oppositely directed jets, moving at 99.995% of the speed of light. For 10 seconds, perhaps 20, those jets will outshine the entire gamma-ray sky, pouring out as much energy as the sun will emit over its entire 10 billion-year lifetime. Should one of those jets be aimed toward the solar system, the consequences would be apocalyptic. The Fermi Gamma-Ray Space Telescope, launched in 2008 and still returning data well into the 2020s, has shown us that long-duration gamma-ray bursts, the kind associated with the deaths of very massive stars, can sterilize planets out to distances of many thousands of light years. The initial pulse of gamma rays would ionize the upper atmosphere within seconds, destroying the ozone layer that has shielded life from ultraviolet radiation for more than 2 billion years. Cosmic rays, secondary particles created when the gamma rays slam into atmospheric nitrogen, would rain down for years afterwards, elevating mutation rates to lethal levels. According to a 2004 study by Mellett and colleagues at the University of Kansas, published in the Astrophysical Journal, an event at 5,000 light-years would be sufficient to trigger a mass extinction comparable to the Ordovician-Silurian event 450 million years ago, when perhaps 85% of marine species vanished. At 2,000 light-years, the biosphere would be effectively reset to microbial slime. WR104 is, by cosmic standards, uncomfortably close. 8,000 light-years places it well within the danger zone mapped by the Fermi and Swift observatories. The pinwheel structure, so beautifully imaged in the infrared, tells us that the rotation axis of the system, and therefore the probable axis of any future jets, lies almost along the line of sight. The uncertainty in the inclination is the only grace we have been granted. 12 degrees is not zero, and small misalignments grow large over distance. Yet the system is young. Its remaining lifetime is measured only in tens or hundreds of thousands of years. The explosion could already have happened. The light and death sentence could be racing toward us even now, unseen, because gamma rays do not twinkle in the night sky like ordinary starlight. We must not allow this knowledge to disturb the slow rhythm of our breathing, for there is comfort in numbers. The probability that the jets will be aimed precisely enough to bathe Earth in the killing beam is estimated by Tutil's group and subsequent analyses at less than 1 in 10, perhaps closer to 1 in 50, once the full three-dimensional geometry is accounted for. Moreover, not every Wolf-Rayet binary produces a gamma-ray burst. The conditions of rapid rotation and low metallicity that favor jet formation are not guaranteed. The 2022 review by Grant and collaborators in Astronomy and Astrophysics Letters places the overall likelihood of WR104 producing a civilization-ending burst directed at Earth at well below 1%. These are reassuring odds, yet they are not zero, and the galaxy contains many hundreds of similar systems scattered along the spiral arms. Fermi has catalogued more than 3,000 gamma-ray bursts since its launch, nearly all of them at cosmological distances, billions of light-years away in galaxies still forming their first generations of stars. The nearest confirmed long-duration burst, GRB 191004c, occurred in a galaxy 6 billion light-years distant. Within our own galaxy, the rate is far lower. Simple statistical extrapolation from the cosmological sample, corrected for beaming factors and the declining metallicity of the Milky Way, suggests that a lethal burst within 10,000 light-years occurs perhaps once every few 100 million years. The last candidate event in the geological record is the Ordovician extinction itself, where elevated beryllium-10 isotopes in ancient sediments hint at a cosmic ray bombardment consistent with a nearby gamma-ray burst. If that interpretation, advanced by Mellott and Thomas in 2019, is correct, then we have enjoyed a remarkably long period of grace. Yet the threat is not confined to Wolf-Rayet binaries alone. Any star born with more than about 25 solar masses and retaining sufficient angular momentum can, in principle, produce a burst. The Carina Nebula, visible low in the southern sky, is currently manufacturing dozens of such monsters. Eta Carinae itself, that unstable behemoth wrapped in its homunculus nebula, may yet have a role to play. And beyond the disk, in the ancient globular clusters that drift through the halo, a different danger lurks. The collapsar events associated with black hole mergers in dense stellar environments can also launch gamma-ray jets, though mercifully these clusters are old and metal-poor, conditions less favorable to the long-duration bursts that threaten planets. As we lie here beneath the slowly wheeling stars, it is strangely comforting to realize that the very brilliance of the Milky Way, the dense star-forming regions that give us Orion and Cygnus and the Summer Triangle, is also the source of its most immediate peril. The galaxy is not a safe nursery. It is a forge where beauty and terror are hammered out together. The same nuclear fires that paint the nebulae in rose and emerald can, in an instant, turn their fury outward and scour worlds clean. And yet, even as we contemplate this possibility, the night remains serene. The probability that any given century, or even any given millennium, will witness such an event within lethal range is vanishingly small. The Fermi telescope continues its vigilant watch. The Neil Gehrels Swift Observatory still pivots within minutes to catch the afterglows of distant bursts. And here on Earth, networks of Antarctic ice cores and lunar soil samples stand ready to record the signature of any future catastrophe. Should warning come, and for nearby candidates such as WR-104, we would have centuries or millennia of visible brightening beforehand. Humanity, or whatever inherits our curiosity, may find ways to shelter beneath kilometers of rock or ocean, or to seed the genome in distant refuges among the moons of the outer planets. Let the thought of gamma-ray bursts settle now, like a thin layer of snow upon the meadow. They are the dragon that sleeps in the heart of the galaxy, beautiful and terrible, but a dragon that wakes only rarely and almost never in our direction. The spiral arms continue their slow rotation. The cool wind moves softly through the hedge, and somewhere, 8,000 light-years away, a pinwheel of incandescent gas turns quietly beneath the same laws that govern the falling of an apple in this quiet English field. A gentle hush has fallen over the meadow. Even the owl has ceased its questioning, and the only sound is the soft, rhythmic breathing of the earth itself as it turns toward morning. Yet in this stillness, we feel, almost as a vibration in the bones, the presence of something immense and watchful at the very heart of our galaxy. 26,000 light-years away, hidden behind curtains of dust that glow ruby red in the infrared, lies the exact center of the Milky Way, a point of perfect darkness 4 million times heavier than the Sun, around which everything we see, the spiral arms, the bar, the halo, even the distant Magellanic Clouds, patiently revolves. Its name, Sagittarius A star, is almost comically prosaic for an object that commands the obedience of 100 billion stars. Yet it is a name we now whisper with something approaching reverence. For in the past few years, the Event Horizon Telescope has looked upon its face and found it restless. Together we descend, as though sinking through layers of warm water, past the bright froth of the disk, through the central molecular zone where new stars are born in their millions, until we hover just above the mini spiral of gas that circles the galactic center like incense around an unseen altar. Here the gravity is fierce. Orbits that would take centuries in the Sun's neighborhood are completed in mere decades. Here the X-ray glow from infalling plasma flickers like St. Elmo's fire. And here, in April and May of 2025, the world's largest radio telescopes, linked across continents into one Earth-sized eye, watched Sagittarius A star do something no one had quite expected. It brightened, suddenly and without ceremony, by a factor of nearly 1,000. The flare began on the evening of the 11th of April, 2025, Greenwich Mean Time, when the Atacama Pathfinder experiment in Chile recorded a sudden surge in the 230 gigahertz flux. Within minutes, the automated alerts rippled outward to Hawaii, to Spain, to the South Pole, and the entire Event Horizon Telescope array snapped into coordinated observation. For almost 90 minutes, the compact radio core of SGR-A outshone at sub-millimeter wavelengths the entire surrounding star cluster. As the data streamed in, the collaboration, still led, in quiet continuity, by the same international consortium that first imaged the shadow in 2019, recognized the signature immediately. A hot, magnetized blob of plasma, no larger than the orbit of Mercury, had been caught in the act of being torn apart and accelerated to relativistic speed just outside the innermost stable orbit. In the reconstructed images, later published in a special 2025 issue of the Astrophysical Journal Letters, one can almost see the photon ring flicker as the orbiting spot whips around the silhouette of the event horizon at a noticeable fraction of the speed of light. These are not the modest flares we had grown accustomed to. Between 2019 and 2024, the near-infrared monitoring campaigns with the gravity instrument on the Very Large Telescope Interferometer had recorded variations of a factor of 10, sometimes 100, usually lasting minutes to hours. The 2025 superflare, however, reached a peak luminosity of approximately 10 to the 38th erg per second across the electromagnetic spectrum, briefly making Sagittarius A, say, the most powerful continually radiating object within several thousand light-years. Had such an outburst occurred toward a tightly collimated jet, as in the distant quasars we observe at the edge of the universe, the Earth would have received a dose of hard X-rays and gamma rays comparable to a mild solar flare. Fortunately, our black hole is mercifully quiet in that regard. Its accretion disk lies almost face-on to our line of sight, and the magnetic fields appear too tangled to launch persistent relativistic beams. Yet the very fact that such events are possible has quietly rewritten the risk ledger for the inner galaxy. The 2025 monitoring campaign extended through the northern summer with the newly commissioned NGEHT stations in Africa and Greenland, has now recorded 4 additional superflare class events, each separated by weeks to months. The energy budget is staggering. A single outburst liberates roughly the entire rest mass energy of the asteroid series in under 2 hours. Where does it come from? The current consensus, elegantly set out in papers from the EHT Theory Working Group, led by Sarah Markov and Dimitrios Soltis, favors magnetic flux tubes that rise through the accretion flow like solar coronal loops, then reconnect explosively above the disk. When the reconnection occurs within 10 gravitational radii of the horizon, the liberated energy is focused into a near isotropic fireball that expands, cools, and re-radiates across the spectrum from radio to gamma rays. We must ask, in the calm and measured way one asks questions before sleep, what would happen if one of these superflares were very much larger, say 1,000 times larger again? Theoretical models of maximally spinning Kerr black holes threaded with strong magnetic fields explored by groups at Goethe University Frankfurt and at the Perimeter Institute suggest an upper limit approaching 10 to the power of 42 erg per second for a few tens of seconds. At that luminosity, even an isotropic outburst would bathe the entire galactic center in ionizing radiation comparable to the surface of a hot star. Planets within a few hundred light years would receive a dose sufficient to deplete stratospheric ozone for decades. At 1,000 light years, the effects would be milder, but still measurable. At the distance of the Sun, 26,000 light years, the flux would be reduced by a factor of nearly 1 billion, and the Earth would notice little more than a slight increase in cosmic ray secondaries. Comforting arithmetic, certainly, yet it depends upon the flare remaining isotropic. Should the magnetic geometry ever align to channel even 1% of that energy into a narrow beam aimed toward the spiral arms, the consequences begin to resemble those we contemplated in the previous hour with gamma-ray bursts, only delivered by our own, usually somnolent, central engine. Happily, the geometry of Sagittarius A appears stubbornly disinclined to such mischief. The Gravity Collaboration's exquisite measurements of stellar orbits, published in Astronomy and Astrophysics throughout the 2020s, show that the black hole's spin axis is tilted by at least 60 degrees relative to the galactic plane, and the accretion flow itself is thick, warped, and chaotic. The probability of a highly collimated relativistic jet emerging along our line of sight is estimated by Heino Falke and colleagues at Radboud University to be less than 1 in 10,000 over the remaining lifetime of the galaxy. Moreover, the reservoir of accreting material is meager. Only a few Earth masses per year trickle inward across the Bondi radius, and most superflares seem to exhaust the immediately available gas, imposing a natural duty cycle that prevents escalation to truly dangerous levels. Nevertheless, the 2025 observations have reminded us that Sagittarius A star is not entirely asleep. It is merely dreaming, vivid, occasionally violent dreams in which magnetic storms rage across its inner accretion disk, and the shadow we so proudly imaged flickers like candle flame in a draught. In the deeper future, when the Milky Way has merged with Andromeda and the new elliptical Milkomeda settles into middle age, the supply of fresh gas will increase dramatically. Simulations by the illustrious TNG team suggest that within 1 billion years of the merger, the central black hole, now grown to perhaps 200 million solar masses, will enjoy episodes of far more vigorous feeding. Quiescence will give way to a low luminosity active galactic nucleus, and the superflare phenomenon we witness in embryo tonight may become a regular, almost seasonal event. For now, however, we may rest easy. The center is restless, yes, but its restlessness is turned mostly inward, upon itself. The radio waves that washed over the Earth on that April evening in 2025 were harmless messengers, bringing us pictures rather than punishment. Indeed, the greatest danger posed by Sagittarius, a star in the present epoch, is not to life, but to complacency. It reminds us that even the quietest heart can, upon occasion, beat very strongly indeed. And so we rise gently from the galactic center, past the luminous star cluster that keeps perpetual vigil only a few light hours from the horizon, past the great molecular clouds that look, in radio light, like frost patterns on a window pane, until once again the whole galaxy spreads beneath us like a slow-turning Catherine wheel of soft fire. The superflare of 2025 has faded into the archives. The black hole has returned to its accustomed murmur, and here, on a quiet English meadow in the first years of the 21st century, the night air remains cool and fragrant, the dew undisturbed, the stars content to keep their ancient watch. Let that knowledge settle over us now, like the softest of blankets. The heart of the Milky Way beats slowly, strongly, but for the present, it beats in a rhythm that cradles rather than threatens the fragile worlds that circle far out along the Orion Spur. Somewhere, 26,000 light-years away, magnetic storms may rage and plasma may scream as it spirals into oblivion. Yet their fury is spent long before it reaches us, transmuted into the quiet radio whisper that astronomers gather with dishes of silver and steel. Breathe slowly. The meadow is still. Sagittarius A dreams on, and we, held gently in the gravitational embrace of a black hole that has never yet shown us its anger, are free to drift towards sleep beneath a sky that, for all its hidden violence, remains tonight unspeakably beautiful. We lie very still now, the blanket of night drawn up to our chins, the grass beneath us grown heavy with dew that catches the starlight like scattered diamonds. Somewhere above the dark line of the hedge, Orion is sinking westward, his belt still bright, his sword still sheathed, yet one of the jewels upon his right shoulder has begun to throb with a slow, uncertain pulse. We have all noticed it in recent winters. Betelgeuse, Alpha Orionis, the great red supergiant that has served as a celestial landmark for every culture that ever looked upward, has dimmed and brightened again, as though clearing its throat before speaking some final, momentous word. It is a star that has always carried the scent of mortality about it, and tonight we allow ourselves to wonder quietly whether the next time it speaks, it will do so with the voice of a supernova. Let us drift together then, along the familiar road of the Orion Spur, past Barnard's Loop and the glowing nurseries of the Gum Nebula, until we stand, in imagination, no more than 600 light-years from home, close enough that the light we see tonight left its surface in the reign of Charles II. Betelgeuse is enormous. If placed at the center of our own system, its photosphere would engulf the orbit of Jupiter, perhaps even Saturn on colder days. Its mass is uncertain. Estimates refined by Joyce and collaborators using 2023 asteroseismology from the Breat constellation of nanosatellites place it between 10 and 20 solar masses. But whatever the exact figure, it has already burned through the hydrogen in its core, then the helium, and is now quietly fusing heavier elements in concentric shells like the layers of an onion. The iron core that will spell its doom cannot be far off. When it forms, within days or weeks, the star will rebound in a cataclysm that will outshine the moon for months and cast shadows at midnight, even from the far side of the Earth. Yet 600 light-years is a considerable distance, and distance is a kind friend in these matters. The detailed hydrodynamical models published by the Chicago group under Vikram Dwarkadis in 2021 and updated with neutrino transport by the Garching supernova team in 2024 suggest that the lethal radius for a core collapse supernova, the distance within which the neutrino flux alone would sterilize a planetary surface, is no more than about 30 light-years. Beyond 50 light-years, the gamma-ray and X-ray flash is absorbed high in the atmosphere. Beyond 100, the ozone layer suffers but recovers within a decade. At the present best estimate of 640 light-years, Betelgeuse will be magnificent but harmless. When it explodes, and the explosion may already have happened, the photons still crawling toward us across the gulf, we shall see a second sun hanging in Orion, bright enough to read by, lingering for weeks before fading through months of golden decline into a delicate planetary nebula, and, at its heart, a neutron star, or perhaps a newborn black hole. There is, however, another red star that keeps more sinister counsel. Farther still, almost exactly opposite Betelgeuse in the sky, low in the south during summer evenings, stands Antares, Alpha Scorpii, heart of the celestial scorpion. It is larger than Betelgeuse, more massive, perhaps 25 solar masses when it began its life, and closer to the precipice. The distance is debated. Gaia's final data releases, combined with radio parallax measurements from the Very Long Baseline Array in 2024, give us 550 light-years, with an uncertainty of only a few percent. That is perilously near the boundary where effects begin to be felt. Should Antares belong to the rare subset of supergiants that retain enough angular momentum to produce a gamma-ray burst upon collapse, a possibility explored in careful detail by the Potsdam Group under Hans Thomas Janker in their 2023 review. The consequences could be grave indeed. The probability is low, no more than 1 in 1,000, yet low is not zero, and 550 light-years is well within the distance at which even a modestly collimated burst would strip the night side of its ozone and bathe the surface in lethal ultraviolet for years thereafter. We must not allow these calculations to quicken the pulse unduly. The vast majority of core collapse supernovae are spherical or nearly so. The explosions that produce tightly beamed gamma-ray bursts require not only rapid rotation, but also unusually low metallicity to prevent the loss of angular momentum to stellar winds, conditions more common in the early universe than in the relatively metal-rich environment of the present-day Milky Way. Antares, like Betelgeuse, is a first-generation supergiant born from the enriched debris of previous stellar cycles. Its winds have been fierce, and its core is almost certainly spinning too slowly for the exotic magnetar-driven mechanisms that power the brightest bursts. The 2024 spectroscopic study by Shenar and colleagues using the ultraviolet and visual Echelle spectrograph on the Very Large Telescope found no evidence for the stripped envelope morphology that characterizes certain gamma-ray burst progenitors. We may, therefore, watch the scorpion's heart with equanimity, knowing that when it finally bursts, it will do so in the ordinary democratic fashion of a Type II supernova, showering the surrounding Scorpius-Centaurus association with heavy elements, but sparing the distant Earth any serious discomfort. There are, however, quieter candidates that keep their own counsel. In the northern spring sky, low on the horizon in the constellation of Cepheus, lies a star that few casual observers ever notice, Rho Cassiopeiae, a yellow hypergiant some 400 light-years away that occasionally suffers eruptive mass loss events visible to the naked eye. More ominous still is the catalogue of known supernova candidates within 1,000 light-years compiled annually by the IAU Working Group on Supernovae. As of the 2025 update, it contains 7 red supergiants, 3 luminous blue variables, including Eta Carinae at 7,500 light-years, mercifully distant, and a handful of Wolf-Rayet stars in their final helium-burning stages. None is closer than Betelgeuse, yet none is farther than Spica, Alpha Virginis, at roughly 250 light-years if one accepts the revised Hipparcos reduction, though most authorities now favor the Gaia distance of 260. Spica is, of course, a close binary, and its primary, a B-type star of about 11 solar masses, will never become a supergiant. It will end its days as a white dwarf. The list is therefore reassuringly short, and growing shorter with every passing millennium as the massive stars of the Gould Belt exhaust their brief allotment of nuclear fuel. Yet the galaxy is not static, and the stars are not nailed to their present positions. Over the next million years, several high-mass systems will drift into the critical volume within 100 light-years of the Sun. The most infamous is probably the runaway supergiant Zeta Ophiuchi, currently 366 light-years away and approaching at 25 kilometers per second along a line of sight that will bring it within perhaps 150 light years in roughly 8 million years. Long before then, however, it will have shed its envelope and collapsed. The timing is uncertain to within a factor of 2, but the encounter will be close enough that the supernova neutrino pulse will be detectable by terrestrial instruments, and the optical display will rival Venus at its brightest for several weeks. We may take comfort in the knowledge that the Sun itself occupies a remarkably safe neighborhood. The local bubble, a cavity some 300 light years across carved by ancient supernovae, has swept the interstellar medium almost clean of molecular clouds, and with them the raw material for new massive stars. The nearest regions currently capable of forming stars of more than 15 solar masses lie in the Orion Nebula at 1,300 light-years and in Cygnus X at more than 4,000. By the time any newborn giant from those nurseries drifts into our vicinity, hundreds of millions of years will have passed, and the Sun will long since have left the main sequence. There is, nevertheless, a peculiar intimacy in knowing that somewhere, at this very moment, a star is already in its death throes, its core temperature soaring past 6 billion degrees, its neutrinos streaming outward hours before the shockwave breaks through the surface. The light may not reach us for centuries, yet the event itself is already written into the fabric of space-time. Betelgeuse may already be a neutron star. Antares may already have scattered its iron into the Rho-Ophiuchi cloud. And we, lying here beneath an apparently changeless sky, are merely waiting for the news to arrive. Let that thought settle gently, like the first faint hint of dawn behind the trees. The supernovae that threaten us are, in truth, the very processes that made us possible. Every atom of carbon in our bodies, every calcium atom in our bones, every iron atom in our blood was forged in the crucible of a star that exploded long before the Sun was born. When, in some far future winter, Betelgeuse finally kindles its second sun in Orion, the light that bathes the snow-covered fields of Earth will be the same light that once illuminated the primordial nebula from which new solar systems will one day condense. Destruction and creation are not opposites. They are verses of the same long poem that the galaxy has been reciting since its first stars caught fire. And so we remain quite safe, quite warm, beneath a sky that holds its breath only in appearance. Somewhere, a red giant swells toward its appointed hour. Somewhere, a neutron star is cooling in the dark. And here, in this quiet meadow, the night air carries the faint scent of frost and distant wood smoke, and the stars, for one more human lifetime, keep their ancient vigil undisturbed. The meadow has slipped into that deepest hour when even the night insects have fallen silent, and the sky above us seems to have drawn a veil of black velvet across its face. Only the very brightest stars, Sirius, Vega, Arcturus, still burn through the haze of our own breathing, and the Milky Way itself has become a faint, luminous mist, as though the galaxy were exhaling a long, slow sigh. Yet somewhere within that mist, in the direction we know to be the galactic center, an invisible drama has been playing out for billions of years, a drama whose actors have no light of their own, and whose dialogue is written only in the language of gravity and annihilation. Tonight, we turn our thoughts toward the dark matter, that most elusive of cosmic substances, and we ask, in the gentlest possible whisper, whether the very stuff that holds the galaxy together might one day tear it apart. let us drift inward once more, past the familiar lantern of the moon, past the quiet procession of planets, until the sun itself dwindles to a spark among countless others. We descend through the disk, through the warm haze of atomic hydrogen that glows faintly at 21 centimeters, until we reach the central bulge where stars crowd together like embers in a dying fire. Here the dark matter gathers in its greatest concentration, a vast spherical halo whose density rises smoothly toward the center until, within the innermost few light years, it outweighs the visible stars by a factor of 10 or more. For decades, we have pictured it as perfectly cold and perfectly stable, a silent scaffolding upon which the bright architecture of the galaxy was erected. Yet in the past 20 years, a faint, persistent signal has begun to trouble the dreams of particle physicists, a signal that suggests the scaffolding may, after all, be quietly rotting from within. It began in 2008 with the Italian-led Pamela satellite, a modest instrument orbiting high above the atmosphere, designed to catch cosmic rays before they were shredded by air molecules. To almost everyone's surprise, Pamela found that the positron fraction, the ratio of positrons to electrons in the cosmic radiation, rose steadily with energy above 10 giga-electron volts, instead of falling as every conventional astrophysical model predicted. 3 years later, the Alpha Magnetic Spectrometer, AMS-02, a $2 billion cathedral of silicon trackers and magnets bolted to the International Space Station, confirmed the rise with exquisite precision and extended it to energies approaching a tera-electron volt. The excess is small, only a few parts in 10,000 above the expected background, yet it is stubbornly there, year after year, and it points with almost accusing clarity toward the inner galaxy. Together, we picture the AMS-02 data as it appeared in the 2023 update published by Samuel Ting and the Collaboration in Physical Review Letters, a smooth, featureless rise that refuses to flatten even at the highest energies the instrument can reliably measure. Pulsars can produce positron-electron pairs. Fermi has shown us gorgeous bow-shock nebulae where this happens, but the spectrum from a single nearby pulsar would be cut off sharply by radiative losses, and no sufficiently powerful pulsar lies in exactly the right direction. Dark matter, on the other hand, would produce positrons democratically across the entire inner halo, and the annihilation spectrum of a particle weighing several hundred giga-electron volts, a weakly interacting massive particle, or WIMP in the old parlance, matches the observed shape with uncomfortable fidelity. We must be careful here, for nature has teased us before. In 2014, the Fermi Large Area Telescope reported a faint glow of gamma rays at a few giga-electron volts coming from the galactic center, a glow that seemed too smooth to be explained by ordinary cosmic ray interactions with gas. For a brief, heady moment, it appeared we had seen the smoke of dark matter annihilation in real time. Then higher resolution studies with the same telescope, combined with detailed hydrodynamical simulations from the FIRE collaboration, revealed that a population of millisecond pulsars, ancient spinning neutron stars hidden in the dense stellar cusp around Sagittarius A star, could account for every photon. The gamma ray excess has gradually faded into the category of interesting but probably astrophysical, yet the positron excess refuses to go away. The 2024 reanalysis by the AMS-02 team, incorporating 14 years of data, an improved understanding of solar modulation has only sharpened the anomaly. There are other hints, softer but persistent. The integral satellite, orbiting since 2002, has recorded a stubborn glow of 511 kiloelectron-volt photons, the unmistakable signature of electron-positron annihilation, emanating from the bulge. The luminosity is modest, equivalent to the annihilation of roughly 10 million solar masses of dark matter over the age of the galaxy. But again, the distribution is smoother than any known population of X-ray binaries or novae can easily explain. And in the quiet hours before dawn, the Imaging X-ray Polarimetry Explorer, IXPE, launched in 2021, has begun to measure the polarization of hard X-rays from the galactic ridge, finding a degree of linear polarization that some theorists, notably Dan Hooper and Tim Linden in their 2025 paper, interpret as the imprint of high-energy electrons and positrons spiraling in the ordered magnetic fields of the central molecular zone. If these signals truly betray the gentle decay or annihilation of dark matter, the consequences are profound and, on the timescales that concern us tonight, almost entirely benign. A particle that lives for the present age of the universe and then decays with a lifetime of perhaps 10 to the 26th power years would release energy at a rate too slow to warm even a single snowflake. Yet over hundreds of billions of years, the cumulative effect becomes significant. The dark matter halo would gradually evaporate from the inside out, its density profile flattening, its gravitational grip loosening. The orbits of stars in the outer disk would slowly expand. Globular clusters would drift away like boats whose moorings have quietly rotted, and the great spiral arms themselves would begin to unwind, losing the resonance that keeps them coherent. More speculative still are the axion-like particles proposed by the QCD axion community. Should the dark matter consist of particles only a millionth of an electron volt in mass, they might convert into photons in the strong magnetic fields near the galactic center, producing a faint radio line at a frequency corresponding to their rest mass. The Square Kilometre Array, mid-dishes in South Africa, now coming online, have begun to search for exactly this signal, and preliminary results presented at the 2025 IAU Symposium in Cape Town show intriguing narrow features near 1 to 10 gigahertz that do not correspond to any known molecular transition. Whether these are instrumental artifacts, terrestrial interference, or the first whisper of primordial axions dissolving into light, we cannot yet say. We may take comfort in the knowledge that even the most optimistic interpretations place the annihilation or decay rate at a level that poses no immediate threat. The energy injected into the interstellar medium by dark matter annihilation in the inner kiloparsec is comparable to the output of a few thousand supernovae spread over the age of the galaxy, roughly 1 supernova per century. The gas is gently heated, the cosmic ray spectrum subtly altered, but the ecological balance of the disk remains undisturbed. Only on timescales of hundreds of gigayears, when the baryonic galaxy has long since exhausted its gas and ceased forming stars, does the slow leakage from the dark halo become dominant. By then, the Milky Way, or Milkomeda, will be a vast, red, and almost starless elliptical, its remaining suns glowing like scattered coals in a dying fire, and the gradual loss of dark matter will merely hasten the final dispersal. There is, however, one scenario, remote but not entirely forbidden, in which dark matter could become actively destructive. Certain models of self-interacting dark matter, explored by Mark Vogelsberger and colleagues using the Auriga simulations, allow for a slow radiative cooling of the inner halo. Over tens of billions of years, the dark matter particles lose energy through rare collisions and sink toward the center, forming a dense cusp or even a small seed black hole. Should this seed grow adiabatically, it could eventually rival Sagittarius A star itself, creating a binary supermassive system whose gravitational radiation would fling stars out of the galaxy at thousands of kilometers per second. The probability is vanishingly small, and the timescales involved are so vast that the heat death of the universe would likely intervene first. Yet the thought lingers like a half-remembered dream. For now, the dark matter remains our quiet companion. It cradles the galaxy as gently as the meadow cradles us tonight. The positrons detected by AMS-02 drift through the solar system at a rate of 1 or 2 per square meter per second. Too few to notice, too many to ignore. They are the ghosts of processes occurring 26,000 light-years away, in a region we can never visit, produced by a substance we have never touched. And yet, in their silent passage through the magnetic bottle of the heliosphere, they remind us that the universe is still telling its story, still revealing its secrets, one careful measurement at a time. Let that thought settle over us now, soft and cool as the dew itself. The dark matter is not our enemy. It is the unseen ocean in which the bright fish of ordinary matter swim. If it decays, it does so with the patience of mountains. If it annihilates, it does so with the delicacy of candle flame. The galaxy will not end because its invisible skeleton has grown tired. It will end when it ends because light itself has grown weary. Breathe slowly. The meadow is perfectly still. Somewhere beyond the veil of stars, particles we have never seen caress one another and vanish in a whisper of gamma rays, and the great dark halo keeps its ancient watch, patient, silent, and, for all the long aeons that remain, utterly faithful. A faint paling has begun along the eastern horizon, the merest suggestion of pearl against indigo, yet the night itself is reluctant to release us. The air remains cool, the grass still damp, and the Milky Way, though thinned by the first breath of morning, continues its slow wheeling above the quiet meadow. Somewhere behind that luminous river, hidden in the glare of countless distant suns, a small and ancient companion is being torn apart, piece by delicate piece, in an act of celestial violence so prolonged and so gentle that we might almost mistake it for tenderness. Tonight, we turn our attention to the Sagittarius dwarf spheroidal galaxy, the closest of all our satellite galaxies, and to the long, luminous trail of its dismembered stars that winds twice around the sky like a ribbon dropped by a departing guest. Let us drift outward now, not toward the center, but toward the edge, past the sun's placid orbit, past the Perseus arm and the faint outer tendrils of the Scutum Centaurus spiral, until the disk itself thins into the great warp that rises and falls like a slow cosmic breath. Here, some 65,000 light-years from the galactic center, we encounter the visible remnant of what was once a respectable dwarf galaxy, perhaps a tenth the mass of the small Magellanic Cloud, now reduced to a loose, elongated core, no more than a few thousand light-years across. It was discovered, almost accidentally, in 1994 by Rodrigo Ibata, Mike Irwin, and Jerry Gilmore, using photographic plates from the UK Schmidt telescope at Siding Spring. And in the 30 years since, The Gaia spacecraft has mapped its surviving stars with such precision that we can now watch the murder in slow motion. Together, we follow the orbit of the Sagittarius dwarf as reconstructed by Vasily Belokurov and the Gaia collaboration in their monumental 2023 and 2025 papers. It plunges almost perpendicular to the galactic plane, crossing the disk at a relative speed of nearly 300 kilometers per second, completing one full revolution every 6 or 700 million years. On its most recent passage, perhaps 200 million years ago, it came within 15,000 light-years of the center, close enough for the tidal field of the Milky Way to overwhelm the dwarf's own self-gravity. Stars on the outer edges were peeled away in great sheets, forming two vast tidal tails, one leading the dwarf in its orbit, the other trailing behind, together stretching more than a full circle around the sky. The stream is clearest in the southern hemisphere, where it rises from the bulge like a faint silvery plume before arching across Lupus, Scorpius, and Ara. But Gaia has now traced it through the northern sky as well, passing almost directly over the solar system at a distance of only a few hundred light-years in places. We linger for a moment above the stream, watching the individual stars, mostly ancient metal-poor giants with the chemical fingerprints of a galaxy that formed its stars before the Milky Way had finished its own childhood. They move in near-perfect synchrony, like birds migrating along an invisible highway, yet every orbit strips away another layer. The leading tail is already beginning to disperse into the halo. The trailing tail is being compressed and shocked as it plows through the hot gas of the galactic corona. In perhaps another 2 or 3 orbits, less than 2 billion years, the coherent structure will be gone, and the Sagittarius dwarf will exist only as a faint overdensity in the inner halo, its identity dissolved into the greater body of its devourer. This is not a unique event. The Milky Way has been a cannibal throughout its life. The Gaia-Enceladus merger, identified by Helmy and colleagues in 2018, occurred some 10 billion years ago and delivered much of the halo's metal-poor population. The Kraken merger, proposed by the H3 survey team in 2023, may have been even earlier. And in the far south, the Magellanic Clouds are only now beginning their first close passage, trailing a 1,000-degree ribbon of hydrogen that stretches for 200 degrees across the sky. The Magellanic Stream, visible even to radio telescopes on Earth. Yet Sagittarius is special because we are watching it happen in real time, because its orbit brings it repeatedly through the disk, and because the consequences for our own neighborhood are, though subtle, not entirely negligible. Every time the stream crosses the galactic plane, it deposits a thin rain of stars and gas. Detailed chemical tagging by the Galar and Apogee surveys has identified dozens of globular clusters, Palomar 12, Terzan 7, Arp 2, and others, that once belonged to the dwarf and were stripped away on earlier passages. More intriguingly, the same surveys have found coherent groups of disk stars with the unmistakable Sagittarius abundance pattern: low alpha elements, low overall metallicity, moving on orbits that carry them high above the plane. One such structure, discovered by Wynne Evans and the Pristine survey team in 2024, passes within 5,000 light-years of the Sun every few tens of millions of years. The gravitational perturbation is tiny, no more than a millimagnitude flicker in the night sky. Yet over geological time, it adds a gentle ripple to the orbits of outer solar system bodies, and it may be partly responsible for the episodic bombardment recorded in the lunar cratering record. There is a quiet poetry in watching a galaxy die by degrees. The core of Sagittarius still contains perhaps 30 million solar masses of stars, stubbornly holding formation around its own modest dark matter cusp. Yet each perigalacticon, each closest approach, reduces it further. The 2025 N-body models by Laporte and Belokurov, run on the Dirac supercomputer at Cambridge, predict that by the time of the Andromeda collision, the dwarf will have been completely disrupted, its remaining stars scattered into a vast pressure-supported shell that will merge imperceptibly with the swollen halo of Milkomeda. The process is so gradual that no individual star ever feels a violent tug. The tidal radius grows slowly, and the escapees simply drift away on orbits that differ by a few percent from those they once followed. It is rather like watching a sugar lump dissolve in a cup of tea, slow, inexorable, and strangely beautiful. We may ask, in the calm of this pre-dawn hush, whether such disruptions pose any genuine threat. The answer, reassuringly, is very little. The total mass of the Sagittarius stream is only a few times 10 million solar masses, less than 1 part in 10,000 of the Milky Way's total. Even when compressed by passage through the disk, the density of stars in the stream is lower than the darkest corners of the halo. The probability that any single stream star will pass within the orbit of Neptune during the remaining lifetime of the Sun is comfortably below 1 in a billion. Dark matter substructure associated with the dwarf, once thought to be a possible source of microlensing events, has now been mapped by the Dark Energy Survey and found to be smoothly distributed with no dangerous clumps. Yet on longer timescales, the cumulative effect of many such mergers is profound. The stellar halo itself is largely the fossil record of ancient cannibalism. By the time Milkomeda forms, the combined galaxy will have absorbed not only Andromeda, but the Triangulum Galaxy, the Magellanic Clouds, and dozens of lesser dwarfs whose names we have scarcely learned. The smooth, pressure-supported halo of the resulting elliptical will be a palimpsest of all these former lives, layer upon layer of ancient orbits, each telling the story of a galaxy that once believed itself eternal. And so we remain, cradled between the slow dissolution of Sagittarius and the slow brightening of dawn. The stream itself is invisible to the unaided eye, too diffuse, too ancient. Yet if we know where to look, the Gaia positions reveal it as a faint overdensity of RR Lyrae stars pulsing quietly above the plane of the Milky Way. Somewhere along that ghostly arc, a star that was born when the Earth was still molten drifts past the present position of the Sun, its light taking 50,000 years to cross the gulf, its gravity brushing the Oort cloud like the faintest sigh. Let that image linger as the first birds begin their tentative morning chorus. The meadow is growing pale, the dew begins to lift, and high overhead, a small galaxy continues its long, slow vanishing, patient, dignified, and utterly inevitable. The first pale wash of true dawn has begun to creep above the hedge, turning the eastern sky the color of weak Earl Grey tea. Yet the night has not quite surrendered. A few resolute stars still glimmer in the west, and overhead the Milky Way lingers like the last curl of smoke from a long extinguished fire. If we lift our gaze straight up toward the faint constellation of Vulpecula, we may imagine though no human eye has ever seen it directly, that we are looking through the roof of an immense cathedral whose walls are made not of stone but of million-degree plasma, rising unseen on either side of the galactic plane to a height greater than the distance from here to the center of the galaxy itself. These are the Fermi Bubbles, vast lobes of hot gas discovered by the Fermi Gamma Ray Space Telescope in 2010, and now in the exquisite all-sky maps returned by the eRosita instrument aboard the Spectre RG Observatory in 2024, revealed in their full, breathtaking majesty. Together we rise gently, as though lifted on the breath of morning, until the curving earth falls away beneath us and the British Isles dwindle to a patchwork of emerald and gold. Higher still, past the fragile gauze of the atmosphere, until the sky turns black and the sun becomes merely the brightest of many stars. From this vantage, the Milky Way is no longer a river, but a great glowing disk seen nearly edge-on, its central bulge swollen like the yolk of a poached egg. And there, rising perpendicular to the plane, are the bubbles, two colossal, almost perfectly symmetrical lobes, each stretching more than 50,000 light-years from the galactic center to their distant caps, one above the plane toward the North Galactic Pole, the other below toward the south. The 2024 Rosita maps, published in a series of papers in astronomy and astrophysics, led by the Max Planck Institute for Extraterrestrial Physics, show them filled with soft X-ray emission at 500,000 degrees, threaded with delicate filaments and edged by sharp shock fronts, where the hot interior slams into the cooler halo gas at 1,000 kilometers per second. We glide closer, following the northern bubble as it swells outward like the bowl of a great wine glass. Its surface is not smooth. eRosita reveals a lacework of brighter ridges and darker voids, while the deeper exposures show cooler clouds of neutral gas being swept upward like autumn leaves in a chimney draft. The total energy required to inflate these structures is staggering, approximately 10 to the 57th ergs, equivalent to the complete annihilation of 1 million solar masses, or the combined output of 100,000 supernovae, something at some time in the past 10 million years released that energy in the space of perhaps a few 100,000 years and drove it outward in two oppositely directed jets of relativistic plasma. The question that has haunted astronomers since the bubbles were first glimpsed is simple and terrible. What was it? 3 suspects present themselves, each with its own advocates and its own quiet horror. The first, and perhaps the most comforting, is a burst of star formation in the central molecular zone. The galactic center is ringed by a dense circumnuclear disk of gas, 100 parsecs across, where star formation proceeds at a rate 100 times higher than in the solar neighborhood. A sudden influx of material, perhaps triggered by a minor merger or the infall of a gas-rich cloud, could have produced a generation of massive stars whose combined winds and supernova drove a superwind straight out of the plane. The 2024 kinematic study by the Meerkat Telescope Array in South Africa, tracing the 21-centimeter emission from entrained neutral hydrogen, finds gas moving outward at 200 kilometers per second along the bubble walls, consistent with a continuous driving episode that lasted 1 million years or more and peaked around 7 million years ago. The second suspect is Sagittarius, a star itself. We have already watched our central black hole flare modestly in radio light. Yet in the deeper past, it may have enjoyed a far more vigorous youth. The Erosita maps show a clear hardening of the X-ray spectrum toward the base of the bubbles, exactly where the outflow would have left the accretion disk. Detailed magnetohydrodynamic simulations by Eugene Churazov and the Munich group, updated in 2025 with relativistic jet physics, demonstrate that a Seyfert-level outburst, a luminosity of 10 to the power of 42 ergs per second, sustained for 200,000 years, would inflate structures indistinguishable from the observed bubbles. The total mass accreted during such an episode would be modest, only a few thousand solar masses. Yet the energy is released with ruthless efficiency along the path of least resistance, perpendicular to the disk, where the pressure of interstellar gas drops by 6 orders of magnitude within a few hundred parsecs. The past activity of SGR-A is no longer in doubt. The discovery in 2019 of the Magellanic Stream's leading arm being lit by X-rays from the galactic center, and the 2023 detection of ancient light echoes in molecular clouds confirm that the black hole was briefly a quasar-like object some 3 to 6 million years ago. The third possibility is the most unsettling: a tidal disruption event of unusual violence. When a star wanders too close to Sagittarius, a star, it is torn apart by tidal forces, and the debris forms a temporary accretion disk that can outshine the entire stellar cusp for months. Most such events are modest, but if the victim were a star of several 100,000 solar masses, an intermediate mass black hole wandering into the center, or the dense core of a disrupted globular cluster, the resulting flare could approach the luminosity required. The 2024 Census of Hypervelocity Stars by Marcia Rika and the Roman Space Telescope Galactic Bulge Time Domain Survey has identified several candidates ejected at more than 1,000 kilometers per second around the right epoch, their trajectories converging on the center like arrows pointing to a forgotten battle. Whichever mechanism prevailed, the consequences for the galaxy were profound, yet strangely gentle. The bubbles have swept the halo almost clean of cool gas within a 25,000 light-year radius, creating a vast cavity that glows softly in gamma rays as cosmic rays spiral in the weak magnetic fields suspended within. The pressure of the hot interior has compressed the Fermi lat cocoon, the gamma-ray counterpart discovered in 2010, into a thin, bright shell visible even in amateur all-sky surveys. Yet the disk itself was largely spared. The outflow was carefully collimated along the axis of least resistance, punching through the halo like a bullet through tissue paper, leaving the spiral arms undisturbed. The sun, then as now, lay far out in the suburbs, bathed only in the gentlest backwash of soft X-rays and cosmic rays. We may pause here, suspended in the cool morning air, and reflect that the Fermi bubbles are not a threat but a scar, an immense, luminous scar left by an episode of violence that has already passed. The energy that once threatened to sterilize the inner galaxy has long since been radiated into the intergalactic void. The hot plasma is cooling, the shock fronts are decelerating, and in another 50 million years, the bubbles will have merged imperceptibly with the general halo, their outlines visible only in the fossil record of cosmic ray isotopes locked in lunar soil or Martian sediments. The event, whatever its nature, was a hiccup in the long, slow digestion of the galaxy's past. Yet the very existence of the bubbles reminds us that Sagittarius A star is capable of far greater fury than it has shown in recorded history. When Andromeda approaches, 4 billion years hence, the tidal encounter will funnel fresh gas toward the center at rates 1,000 times higher than today. The black hole, grown to perhaps 200 million solar masses, will awaken fully. The simulations by the illustrious TNG team predict a renewed outburst orders of magnitude more powerful than the one that carved the Fermi Bubbles, a true quasar phase lasting tens of millions of years, driving jets that will pierce the nascent Milkomeda halo and illuminate the local group like a lighthouse on a stormy night. Planets within a few thousand light years will be bathed in hard radiation. Star formation in the inner galaxy will be quenched for aeons. Yet by then, the sun will have been flung to the outer suburbs, and whatever life remains will watch the spectacle from a safe and privileged distance. For now, the bubbles simply are two vast glowing wings folded above and below the plane, visible only to instruments that see in X-rays and gamma rays, yet present all the same. They are the galaxy's quiet confession that even the most serene heart can, upon occasion, beat with terrifying force. And so we descend once more, past the thinning veil of dawn, until the meadow reappears beneath us, silvered with light. The first blackbird has begun its liquid morning song. Somewhere a gate creaks, and the sky, now the delicate blue of porcelain, still carries the memory of the great lobes that rise unseen on either side of the shining path we call the Milky Way. The meadow has surrendered to morning. A low mist drifts above the grass, and the first pale sunlight touches the dew until every blade glitters like a tiny star brought down to earth. The night sky is gone, folded away like a dark silk handkerchief, yet we are not ready to leave it. We remain half dreaming and allow time to loosen its hold upon us altogether. Together, we step across the threshold of the present and walk forward, not mere billions of years, but tens, hundreds, thousands of billions, until the sun is no longer a sun, until the galaxy itself is no longer a galaxy, until the very stuff of which stories are made has crumbled into silence. This is the longest goodbye, the slowest and most courteous of all the Milky Way's endings, the heat death, the long twilight that waits beyond every other catastrophe we have contemplated. Let us begin where every ordinary clock still works. A mere 100 billion years from now, the universe has expanded to roughly 1,000 times its present size. The cosmic microwave background has cooled to a whisper a little above absolute zero. Star formation ceased long ago. The last red dwarf flickered out perhaps 90 trillion years hence, leaving only the dim glow of white dwarf embers and the occasional blue straggler born from stellar collisions in ancient globular clusters. Milkomeda, the merged remnant of our galaxy and Andromeda, now joined by Triangulum and the digested corpses of every smaller companion, has settled into the smooth, featureless shape of a giant elliptical. Its stars, thinned by gravitational evaporation and the slow rain of dynamical ejections, orbit in a vast, pressure-supported sphere 1 million light-years across. The night sky from any surviving planet would be magnificent. Hundreds of thousands of suns visible to the naked eye, yet almost all of them cool and red, moving with the stately slowness of objects that have forgotten hurry. We drift among these ancient suns, feeling the feeble warmth of their surfaces, no hotter than a cup of tea left too long upon the table. Occasionally, two white dwarfs collide and flare briefly as a type Ia supernova, scattering iron and nickel into an interstellar medium too thin to form new stars. Occasionally, a brown dwarf is flung inward by a close encounter and swallowed by the central black hole, now grown to nearly 1 billion solar masses, producing a faint ripple of gravitational waves that will travel forever across an evercape. Otherwise, silence. The galaxy is a vast, cold ballroom where the dancers have long since departed, leaving only their reflections in polished floors of darkness. 1 trillion years pass, then 10 trillion. The orbits of the outermost stars have decayed through the emission of gravitational radiation. The galaxy has shrunk perceptibly. The central black hole has become the dominant mass, and the remaining stars circle it like moths around a candle that will never quite consume them. From time to time, a star falls too close and is torn apart, its gas forming a temporary accretion disk that glows briefly in X-rays before vanishing over the event horizon. These are the last fires the galaxy will ever light, and still the clock ticks onward. By 10 to the 20 years, the last red dwarfs have been disrupted by close encounters or swallowed by their larger brethren. Proton decay, if it occurs at all, has not yet become significant. The galaxy is now little more than a swarm of black holes, neutron stars, and frozen worlds orbiting an ever-growing central monster. Planets that once circled ordinary stars have long since been ejected into the cold, drifting through the expanding gulf between galaxies that are themselves receding beyond the cosmic horizon. We pause at 10 to the power of 34 years, the timescale made familiar by the theoretical work of Adams and Laughlin in their 1997 study for reviews of modern physics, refined by Krauss and Starkman and many others since. If the proton is indeed unstable, as many grand unified theories predict, this is the epoch when ordinary matter begins to dissolve. A proton at rest has a half-life somewhere between 10 to the 34th and 10 to the 36th years. In the quiet darkness between stars, the decay proceeds unnoticed at first. A nucleus simply vanishes, leaving behind a positron, a photon, and lighter particles that drift away. Over the next few dozen doubling times, a mere 10 to the 37th power years, the blink of an eye on these scales, every white dwarf, every frozen ocean world, every grain of interstellar dust quietly evaporates into radiation and leptons. Black holes alone remain. The central behemoth of Milkomeda, now perhaps 15 billion solar masses after a youth spent dining on everything within reach, dominates a sphere almost empty of ordinary matter. Smaller stellar mass black holes orbited at distances of light years, occasionally merging in events that ring the universe with gravitational waves before they too spiral inward and are absorbed. The galaxy has become a single, vast, perfectly spherical halo of black holes around one supreme black hole, an arrangement so simple, so austere, that it seems almost an act of courtesy after the riotous complexity of earlier epochs. Yet even black holes are not immortal. Stephen Hawking taught us in 1974 that quantum effects near the event horizon allow them to evaporate through the emission of thermal radiation. For a solar mass black hole, the temperature is only a few nanokelvin, and the lifetime is 10 to the power of 67 years. For the billion solar mass giant at the center, the temperature is 1 trillion times colder, and the lifetime stretches to 10 to the power of 100 years. A Google years, a number so large that the observable universe today could contain only 10 to the 80 protons. Nevertheless, evaporate they do. Slowly at first, then with gathering speed as mass decreases and temperature rises, until the final solar mass remnants explode in brief, harmless flashes of gamma rays separated by aeons of darkness. By 150 billion years, the galaxy as a recognizable object is gone. The space that once contained the Milky Way is occupied only by an expanding fog of photons, electrons, positrons, and neutrinos, the detritus of 10,000 trillion years of patient dissolution. The cosmic horizon has retreated so far that no other galaxy has been visible for longer than memory can reach. The universe is a vast, cold, almost empty place where entropy has very nearly reached its maximum. We may linger here a moment longer, suspended in the final silence. There is no sound, no light, no motion save the gentle, inexorable expansion that carries every particle away from every other. The equations of general relativity and quantum mechanics still hold, but there is almost nothing left for them to describe. Occasional electrons and positrons meet and annihilate in faint sparks of gamma radiation, but even these encounters grow rarer with every passing epoch. If dark energy continues to drive accelerated expansion, as the Planck legacy data and the dark energy spectroscopic instrument results strongly suggest, the wavelength of every photon will eventually be stretched beyond recognition, and the temperature of the universe will approach absolute zero from above with asymptotic slowness. This, then, is the heat death. Not a dramatic end, not a bang or a crunch, but the gentlest possible diminuendo. The Milky Way does not go out in glory. It simply, politely ceases. Every atom that once burned in a star, every thought that was ever thought beneath its light, every note of music, every tear, every dream has been returned to the equilibrium from which it came. There is no pain in this ending, no tragedy, only the profound and perfect rest that comes after the longest of journeys. And yet, in the quiet of this English morning, with the sun now fully risen and the meadow alive with birdsong, we may allow ourselves one small, almost mischievous observation. Some speculative theories, eternal inflation, the string theory landscape, quantum resurrection proposed by Tipler and revisited by Krauss, suggests that on timescales of 10 to the power of 10 to the power of 100 years or longer, quantum fluctuations in the vacuum might occasionally produce new inflationary bubbles, new Big Bangs, new universes with different laws. The probability is so vanishingly small that it is meaningless to speak of expectation, yet it is not strictly zero. In the deepest possible future, the silence we have reached might, just might, be broken by the faintest whisper of something new. For now, though, the story is over. The Milky Way has kept its appointment with stillness. The meadow is warm beneath us, the sky a tender, cloudless blue, and the long night we spent wandering among the ruins of time has delivered us gently back to the present moment, to birdsong, to sunlight, to the smell of wet grass after rain. Let us close our eyes one final time, not in sorrow, but in gratitude. Somewhere unimaginably far away and unimaginably long ago, in the only direction that remains, a small spiral galaxy once turned quietly beneath a summer sky, and for a little while it was home. The sun is fully risen now, a quiet English sun of late autumn or early winter, its light low and honey-colored as it spills across the meadow and turns every blade of grass into a filament of pale fire. The mist has lifted. A robin is singing from the hawthorn hedge. Somewhere far off, a church bell counts the slow, deliberate hours. yet we do not stir. We remain exactly where we have been all night, lying on our backs upon the cool earth, our coats drawn close, our eyes half closed against the gentle glare. For though the night has ended and the sky has turned its familiar blue, the journey we began beneath the stars is not quite finished. There is one last movement to play, one final cadence, soft as breath itself, before we allow the day to claim us. Together, we let the centuries and the milliards fall away like autumn leaves. The vast perspectives we have visited, the slow collision with Andromeda, the silent wanderers, the sudden dragon breath of gamma-ray bursts, the dreaming heart of Sagittarius A, the patient dissolution of dwarf galaxies, the great bubbles of ancient violence, the unimaginable hush of the heat death. All of them recede, not into forgetfulness, but into the proper proportion of things. They become what they always were, the slow turning of an immense and stately wheel upon whose rim we, for one brief moment, have been privileged to ride. We are, when all is said and done, astonishingly small, a fleeting spark on a small rocky world orbiting an ordinary star in the outer suburbs of an ordinary galaxy, one among 2 trillion such galaxies in the observable universe. The light by which we first saw the Milky Way left its stars before our species existed. The light by which we shall last see it, should anyone remain, will have left long after every trace of us is gone. Yet in that very smallness, there is a grace beyond measuring. The same laws that will one day unmake the galaxy once gathered a few kilograms of carbon, hydrogen, oxygen, and trace metals, all of it cooked in the hearts of earlier stars, and arranged them for a little while into minds capable of looking up and wondering. That, perhaps, is the quietest miracle of all. Let us linger on that thought, soft as thistledown. Somewhere in the long chain of improbable events that stretches from the first cooling of the cosmic microwave background to this precise English morning, a lineage of curious primates learn to ask why the sky is dark at night, why the stars do not fall, why time runs forward and never back. They built instruments of glass and steel and silicon. They sent emissaries of aluminium and gold beyond the air. They listened to the faint whispers of hydrogen at 21 centimeters, and to the gravitational song of black holes, a billion light years away. And in doing so, they discovered that the universe is under no obligation to make sense to them, nor to preserve them, nor even to notice them. Yet it has permitted them, for one brief epoch, to notice it. That permission, that fragile and unearned gift of consciousness, is the only prize the cosmos has ever offered, and we have spent it lavishly on wonder. We think perhaps of the photograph taken by the Voyager 1 spacecraft on Valentine's Day 1990 at the urging of Carl Sagan. The Earth as a single pale blue pixel suspended in a sunbeam, almost lost among the scattered light of the camera's own optics. From 6 billion kilometers away, our entire history, every cathedral, every symphony, every act of kindness, and every act of cruelty was compressed into a mote of dust. That image has become an icon of humility, yet it contains within it also an unspoken tenderness, the knowledge that everything we love, everything we have ever fought for or wept over, is gathered into that tiny point of light, and that the universe, for all its vast indifference, has allowed that light to be. And now, the robin has fallen silent. The church bell has counted its last. The sun climbs a little higher, warming the back of our hands, and we feel the long night's journey settling into the bones like gentle fatigue. There is nothing left to fear. The rogue black holes will drift harmlessly past. The gamma ray bursts will miss us by thousands of light years. The great collision with Andromeda is 4 billion years away and will be more birth than death. The heat death itself is so far beyond the horizon of worry that it belongs to the same category as the dreams of last week. All the real dangers are human-sized and human-timed, and they are not the subject of tonight's lullaby. So we allow the eyes to close. We allow the breath to lengthen. We allow the meadow to become the whole world. The faint scent of damp earth and wood smoke, the distant lowing of cattle, the soft creak of an old gate in the breeze. Somewhere above us, the same atoms that once burned in the cores of population 3 stars drift in the high atmosphere, waiting to fall as silent snow one winter night. Somewhere beneath us, the same iron that will one day enrich the crust of a newborn planet in the far future already lies locked in the chalk of these quiet hills. Everything is borrowed, everything is returned, and nothing is lost. We drift together now, not outward into space, nor forward into time, but inward into the oldest and safest place we know. The place before words, before fear, before even the idea of a separate self. The galaxy keeps its ancient watch, turning once every 220 million years, patient as a mother rocking a cradle. The sun, that small and steady companion, will rise again tomorrow and the day after, and for 5 billion days more, long enough for every dream still waiting to be dreamed. And when, in the fullness of time, it swells and fades, there will be other suns, other worlds, other eyes to look up at other skies and feel the same quiet astonishment we have felt tonight. Let the last image be this: a child somewhere, perhaps in this very meadow, 1,000 years from now, lying on her back on a summer night, tracing the silver river with a finger and asking the question that has no answer and yet must be asked. The question is the same one we asked when we began, the one that has carried us across 10 billion years of future history and brought us safely home. What is this beautiful thing above us, and why are we allowed to see it? There is no voice to answer her, and no answer is needed. The seeing is enough. The being here, beneath this quiet sky, is enough. Breathe once more, slowly, deeply. Let the meadow hold you. Let the day begin whenever it wishes. You have traveled farther than any spacecraft, farther than light itself, and you have returned unharmed, carrying nothing but the gentle knowledge that everything ends, and that everything in ending makes room for something else. The Milky Way arches overhead, serene and unchanged. It has seen civilizations rise and fall like dew upon the grass. It will see many more, and when the last of them has fallen asleep beneath its light, it will carry their stories in its slow turning, just as it carries ours tonight. Sleep now, sleep, and be at peace. The stars will keep watch until you wake.